Beneath the silence of the night sky lies a secret ocean. It has no color, no surface, no horizon. It cannot be sailed, nor stirred, nor drained. Yet it stretches everywhere, infinite and unbroken, filling the chasms between galaxies, seeping into every particle, woven into the very bones of space-time itself. Galaxies drift across it like islands adrift on a black sea. Stars burn like sparks above its fathomless deep. Every atom, every force, every equation that sustains reality rises and falls upon its unseen tide. The cosmos is not built upon emptiness, but upon this invisible ocean. For ages, humanity mistook the void for nothing. Yet physics revealed otherwise. Even where matter is absent, something trembles. A restless storm of quantum fields, alive with ghostly particles flashing in and out of being. Nothingness is not still. It is a sea forever whispering. But the ocean is not merely background. It is scaffolding. It gives mass to particles, anchors the architecture of matter, and drives the expansion of the universe itself. It is the unseen current that holds the cosmos together, and perhaps, one day, could pull it apart. Yet unease deepens with each discovery. When theory attempts to weigh this ocean, its predicted energy is vast beyond comprehension. When astronomers measure it in the sky, it is almost vanishing. The greatest discrepancy in all of science. Here lies the paradox. The ocean is everything, and yet it evades understanding. Is it creation's hidden reservoir, a storm that has no end, or the silent seed of destruction yet to come? The story begins here, in the silence of the void, where nothingness is not empty, but alive. For as long as human beings have tilted their heads to the heavens, the question of emptiness has lingered. Was the space between stars truly nothing, or was it something unseen, something that refused to give itself away? In the age of ancient philosophy, the void was a subject of suspicion. Aristotle, observing the order of nature, rejected the idea of the vacuum entirely. He declared that nature abhors a vacuum, insisting that emptiness could not exist, that space must be filled with substance, with air, with something. The atomists, by contrast, dared to imagine the universe as particles drifting in a boundless void, an infinite sea in which matter swam. For centuries, the debate endured not merely about physics, but about existence itself. With the rise of modern science, the question evolved. In the 17th century, Isaac Newton envisioned a universe governed by gravity, planets tracing orbits around the sun in a space that was absolute and unchanging. For Newton, the void was real, an infinite stage upon which the drama of matter unfolded. Space was the silent background, the immutable theatre where forces acted and particles moved. To him, it was emptiness, but emptiness endowed with permanence. Centuries later, that view began to unravel. Albert Einstein, with his general theory of relativity, transformed space from stage to actor. No longer a passive void, space-time became a dynamic fabric, bending and curving in response to energy and mass. Matter told space-time how to curve, and curved space-time told matter how to move. Emptiness was not empty. It was geometry, alive and malleable. The void itself could bend, yet even Einstein underestimated its depths. In the early 20th century, as physicists probed the atom, they discovered a stranger truth. Beneath matter lay the rules of quantum mechanics, and within those rules, the vacuum itself refused to stay still. Max Planck revealed that energy came in quanta, indivisible packets. Werner Heisenberg showed that uncertainty haunted every measurement, forbidding exact knowledge of a particle's position and momentum. Niels Bohr described the atom as a blur of probabilities, a dance of electrons that could never be pinned in place. The lesson was clear. Even at the smallest scales, nature was restless. From this new perspective emerged the quantum vacuum. In 1930, Paul Dirac introduced the concept of the sea of negative energy. He suggested that beneath reality lay a boundless ocean of invisible states, filled with particles occupying every level below zero. A hole in this sea would appear as a particle, the first glimpse that the vacuum might not be void, but full. Then came proof. In 1948, Dutch physicist Hendrik Casimir proposed an experiment so delicate it seemed almost impossible. Placed metal plates, polished and parallel, a few micrometers apart. If the vacuum were truly empty, nothing should happen. But Casimir predicted otherwise. Invisible waves of quantum fluctuation, excluded between the plates, would create a pressure difference. The plates, suspended in nothing, would be pushed together by the energy of the vacuum itself. When the experiment was performed, his prediction held. Nothingness had forced another fingerprint followed. In the hydrogen atom, the electrons' orbit was predicted with exquisite accuracy, but in 1947, Willis Lamb discovered a tiny deviation, a subtle shift in energy. The culprit was not matter, but vacuum fluctuations. The electron, buffeted by the trembling sea of space, moved differently than expected. The Lamb shift became further proof. The void was alive, an ocean that could tug upon particles. By the mid-20th century, cosmology deepened the riddle. Edwin Hubble, observing distant galaxies, revealed that the universe was expanding, that the sky itself was stretching. To explain why it did not collapse, Einstein once introduced the cosmological constant, a mysterious energy in space that repelled matter. He later abandoned it, calling it his greatest blunder. Yet decades later, the concept returned. Perhaps the vacuum itself held energy, woven into space-time, shaping the cosmos. This realization forced a reckoning. The vacuum was not nothing. It was a field, a stage of ceaseless motion, a hidden ocean whose influence extended from atoms to galaxies. The Casimir force, the Lamb shift, Einstein's constant, the restless fields of quantum theory, all pointed to the same conclusion. What humans once called emptiness was the very medium of existence, and the more it revealed, the more unsettling it became. For if the vacuum had energy, then it might dominate the fate of the universe. It might drive cosmic expansion. It might decide whether the cosmos drifts forever, collapses in ruin, or collapses into something stranger still. The discovery phase ended with awe and unease entwined. The void, once dismissed as absence, had become presence. The ocean of energy was no longer speculation. It was written into experiments, into equations, into the expansion of the cosmos itself. Humanity had peered into nothing and found everything. The discoveries of the 20th century had revealed that the vacuum was not empty, but restless, an ocean of invisible activity. Yet the deeper physicists looked, the more the void betrayed them. What emerged was not a harmonious picture, but a contradiction so immense that it threatened the very foundation of science. The first shock came with the revelation of zero-point energy. According to quantum mechanics, every field that permeates reality retains a minimum energy, even at absolute zero. No matter how cold, no matter how still, fluctuations cannot be erased. The uncertainty principle forbids silence. Particles tremble, in and out of existence, ghost-like, borrowing energy from nothing and returning it in an instant. This restless hum is called vacuum energy, the irreducible pulse of the universe. Experiments confirmed it. Quantum electrodynamics, the theory, uniting light and matter, demanded that vacuum fluctuations alter the behavior of electrons. Calculations predicted minute shifts, and experiments such as the Lamb shift and anomalous magnetic moments confirmed them to extraordinary precision. Quantum theory, when applied to the vacuum, produced results correct to 10 decimal places. Nothingness was not speculation. It was measurable, testable, real. But when cosmology entered the picture, the harmony fractured. If the vacuum is filled with energy, then it should gravitate. According to Einstein's equations, energy curves, space-time, vacuum energy, spread evenly across the cosmos, would act as a repulsive force, a cosmological constant accelerating expansion. Physicists attempted to calculate its value, summing the contributions of every quantum field. The result was catastrophic. The numbers predicted that the energy density of the vacuum should be 10 times larger than observation. A value so vast it would have torn the universe apart instantly, preventing galaxies, stars, or life from ever forming, yet the cosmos existed. The prediction was wrong by the largest margin in all of science. This cosmological constant problem became known as the worst theoretical failure ever recorded. For decades, the contradiction loomed. Either quantum field theory was incomplete, or something miraculous cancelled nearly all of the vacuum energy, leaving behind only the faintest remnant. The universe seemed fine-tuned, balanced on a knife's edge between nothingness and explosion. Then, in 1998, came the discovery that transformed unease into terror. Teams observing distant supernova standard candles scattered across billions of light-years measured how their light dimmed with distance. The expectation was that cosmic expansion should be slowing under gravity's pull. Instead, the data revealed the opposite. The expansion of the universe was accelerating, as though pushed by an unseen hand. The culprit, dark energy, a force indistinguishable from vacuum energy itself. The ocean of nothingness was not merely a background, it was driving the fate of the cosmos, tearing galaxies apart. Suddenly, Einstein's abandoned cosmological constant was resurrected, no longer a blunder, but a necessity. The vacuum was alive and expanding, its pressure greater than gravity's pull. The shock reverberated. If vacuum energy truly dominates, it dictates the ultimate destiny of the universe. Stars may burn out, galaxies may drift into darkness, and the cosmos may stretch into eternal isolation. The void, not matter, rules. But the paradox sharpened further. The tiny observed value of dark energy, 120 orders of magnitude, smaller than theory predicted, demanded explanation. Why is the vacuum almost empty, but not quite? Why does it contain just enough energy to accelerate? Expansion, but not enough to prevent galaxies from forming. It seemed too precise to be coincidence. Physicists began to whisper of fine-tuning, of anthropic principles, of universes beyond our own, where vacuum energy takes different values. In most, no life could exist. In this one, by accident or design, the vacuum allowed stars to shine and observers to ask questions. The void had become not just a scientific puzzle, but an existential riddle, and with it came dread. For if the vacuum holds energy, it might also hold instability. Quantum field theory allows the possibility that our vacuum is not the true ground state of reality, but a false vacuum, metastable and temporary? If so, it could decay, collapsing into a lower energy state. A bubble of new physics could appear anywhere, expanding at near light speed, rewriting the laws of nature as it spread. Protons might decay, atoms dissolve, light itself change character. Existence would end without warning, in silence. The possibility is speculative, but consistent with what is known. The Higgs field, discovered in 2012, appears to place our universe near such a metastable boundary. Though the timescales may be vast, the threat is embedded in the equations. The ocean of energy that sustains reality may also conceal its undoing. The shock, then, is double. On the one hand, the vacuum is too strong. Theory predicts infinities, catastrophic energy densities. On the other, it is too weak. Observations show only the faintest whisper. Between these extremes lies our universe, precariously balanced, as if by improbable chance. The laws of physics, triumphant in so many domains, here confront their greatest contradiction, and so the scientific shock lingers. Nothingness is not empty, yet it defies comprehension. The vacuum is measurable, yet inexplicable. It holds galaxies together, yet pushes them apart. It is a foundation that may collapse. It is an ocean whose depths resist all soundings. Humanity once feared the emptiness of the night sky. Now it fears the fullness of the void. For in the ocean of energy lies both the proof of existence and the shadow of annihilation. The shock of the vacuum's paradox left physics trembling. If the ocean of energy was real, and all evidence suggested it was, then its nature had to be pursued, mapped, and dissected. The task demanded not only theory, but observation, experiment, and the steady patience of instruments tuned to whispers from the void. The first clues came from the oldest light in the universe, the cosmic microwave background. In 1965, Arno Penzias and Robert Wilson discovered this faint glow, a remnant of the Big Bang. Decades later, satellites such as COBE, WMAP, and Planck mapped it with exquisite detail. What they found were not uniform skies, but tiny fluctuations. Temperature differences of only 1 part in 100,000. These subtle ripples carried the fingerprints of quantum fluctuations from the infant universe, inflated by cosmic expansion. These tiny quantum jitters grew into the seeds of galaxies, clusters, and the vast cosmic web. In the frozen patterns of the microwave background, the storm of the vacuum had left its mark, shaping the universe's very architecture. To measure those ripples was to glimpse the ocean in its earliest tide. Another set of clues emerged in the distribution of galaxies themselves. Astronomers discovered faint rings, fossil imprints of baryon acoustic oscillations, sound waves that once rippled through the hot plasma of the young cosmos. These waves froze when matter and light decoupled, leaving behind a scale imprinted across space. Measuring these frozen echoes allowed cosmologists to map expansion over billions of years, tracing the influence of dark energy with increasing precision. Yet the vacuum revealed itself not only on cosmic scales, but within the laboratory of the atom. In 1947, Willis, Lamb, and Robert Rutherford observed a minute shift in hydrogen's spectral lines, a deviation from predictions that could only be explained by vacuum fluctuations. The so-called Lamb shift became one of the first experimental proofs that the void alters reality at the quantum level. Similarly, the Casimir effect, discovered in 1948, showed that two metal plates brought close together experience a measurable attraction, not from ordinary forces, but from the suppression of vacuum modes between them. In these fragile experiments, the invisible ocean made itself known as a force that can be weighed. As particle physics advanced, the discovery of the Higgs boson in 2012 offered another doorway into the storm. The Higgs field is not merely a mathematical abstraction. It is a background that fills space, bestowing mass on fundamental particles. Without it, electrons would be massless, atoms impossible, chemistry non-existent. The Higgs confirmed that reality is built upon invisible fields, vast and pervasive. Its discovery sharpened the question: if one field can fill all of space, could the vacuum itself be a patchwork of such hidden seas, layered and interwoven? Black holes offered yet another lens. In 1974, Stephen Hawking shocked physics with his prediction that black holes radiate. According to his calculations, the intense warping of space-time at the event horizon forces the vacuum to reveal itself, producing pairs of virtual particles where one falls in and the other escapes. Over time, this Hawking radiation could cause black holes to evaporate. If true, it confirmed that the vacuum is not only alive, but inseparably tied to gravity itself. Even at the edge of destruction, the ocean of energy continues to speak. Other phenomena point toward the same conclusion. Vacuum polarization, the way virtual particles shield electric charges, subtly shifts the strength of forces. Neutrinos, relics from the earliest seconds of the cosmos, may still swim through space as part of a hidden background sea, their ghostly presence woven into the fabric of the void. Simulations have pushed the mystery further still, using physicists model universes filled with quantum fields, watching how structures evolve under different vacuum energies. The results are startling. If the vacuum's energy was slightly larger, galaxies would never have formed. Slightly smaller, and the universe would have collapsed. Our cosmos appears balanced at the narrowest possible threshold, as though reality itself were fine-tuned upon a razor's edge. But perhaps the most profound investigation does not ask how the vacuum influences matter, but whether matter itself emerges from the vacuum. Some theorists propose that space-time geometry is not fundamental, but arises from quantum entanglement. In this vision, the web of connections between particles, the correlations of quantum information, is what weaves the very fabric of space. The ocean of energy is not something inside space-time. It may be the loom from which space-time is spun. The deeper science has probed, the more paradoxes appear. Inflationary theory suggests that in its earliest instant, the universe underwent a burst of expansion driven by vacuum energy, growing faster than light, creating the cosmos as we know it. Yet, if inflation is true, it may not have stopped. Everywhere, some regions may still be inflating, eternally, spawning new universes beyond our horizon. The ocean of energy may not only hold our universe together, but give birth to countless others in an endless storm. The evidence accumulates like overlapping waves, microwave ripples from the Big Bang, frozen sound waves in the cosmic web, subtle laboratory shifts, the glow of evaporating black holes, the geometry of space-time itself. Each experiment, each observation, is a fragmentary map of an invisible sea, and still, the central contradiction remains unsolved. The vacuum is vast, yet small, violent, yet delicate, foundation, yet potential destroyer. The investigations deepen, but the ocean refuses to yield its final truth. What, then, is this energy that hums through nothing? Is it the last remnant of creation's fire, the scaffolding upon which galaxies are built, or the seed of their annihilation? Every instrument, from telescopes peering into ancient light to colliders smashing particles apart, converges on the same riddle. The void is not empty. The void is alive, and the deeper science looks, the deeper the mystery grows. The ocean of energy had revealed its fingerprints across scales, from the hydrogen atom to the horizon of the cosmos. Yet the further physicists pressed, the more unsettling the picture became. The storm was not gentle. It was vast, unbalanced, and potentially unstable. What began as subtle ripples in empty space grew into a profound existential riddle. The first escalation came with dark energy's dominance. In 1998, distant supernova revealed that cosmic expansion was not slowing, as gravity would dictate, but accelerating. It was as though the vacuum itself were pushing outward, stretching space-time faster with every passing epoch. Over time, this outward thrust would overwhelm matter. Galaxies not bound to us by gravity would recede beyond reach. Already, billions of galaxies have slipped beyond our cosmic horizon, their light stretched into invisibility. In the future, only our local group, the Milky Way, and its nearest companions will remain visible. The sky itself is vanishing. This realization transformed the ocean from background into master. Matter and radiation, once dominant, now make up only a fraction of the universe's energy budget. Dark energy, the ocean's silent current, commands the cosmos. Its grip grows stronger with time, rewriting the fate of all things. But acceleration was only the beginning. Theoretical physics soon raised a more terrifying possibility, that our vacuum is false. In quantum field theory, a field can rest in a metastable state, a valley that is not the lowest possible. If the Higgs field, which gives particles mass, is metastable, then the vacuum itself is precarious. A deeper state could exist, one of lower energy, waiting silently. If a quantum fluctuation or high-energy event were to trigger decay, a bubble of true vacuum could form. The consequences are unspeakable. The bubble would expand at nearly the speed of light, rewriting the laws of physics as it swept through. Atoms would dissolve, forces would shift, even space-time itself would be remade. There would be no warning, no escape, only sudden annihilation. The frozen ocean of energy would become a tidal wave, drowning existence in silence. Though calculations suggest such decay may not occur for trillions of years, the possibility lingers like a shadow. The universe, it seems, is not only fragile, but perched on a precipice. Escalation deepens further in the concept of eternal inflation. If inflation in the early universe was driven by vacuum energy, then in some regions it may never have ended. Space there would continue to expand exponentially, birthing pocket universes in an endless froth. Our cosmos would be just one bubble in an infinite sea, unreachable and disconnected from the rest. The ocean of energy would not merely hold our universe together, it would be the womb of countless universes, each with different laws, each unknowable. The philosophical weight of this vision is immense. If true, then most of reality is forever. Beyond us, hidden not by distance, but by disconnection. The unreachable becomes not a frontier to be crossed, but a permanent condition of existence. Humanity lives in a fragment, a single eddy in an infinite storm. Other theories escalate the dread. Some physicists propose that space-time itself is emergent, born from patterns of quantum entanglement. If so, the ocean is not only energy, but information, the fundamental weave from which geometry itself arises. But if that weave frays, what becomes of space and time? The foundation is not stone but tapestry, fragile and dependent on unseen threads. Even within black holes, the storm refuses to rest. Hawking's paradox of evaporation collides with quantum mechanics, suggesting that information might vanish. Yet theories of holography argue the opposite, that the information of everything swallowed by a black hole remains encoded on its surface. If so, then the ocean of energy is not only alive but conscious of itself, storing memory at the edges of horizons. The vacuum may not be an absence but a vast archive. Each of these escalations transforms unease into awe and awe into fear. The ocean of energy is not a quiet background but an active architect. It drives the expansion of space, seeds galaxies, weighs upon particles, whispers at horizons, and may one day end the universe. Its role is not optional, it is central. Without it, nothing exists, and yet with it, existence may not endure. For cosmologists, this escalation is not merely theoretical. Observations continue to confirm dark energy's presence with increasing precision. The cosmic microwave background, baryon acoustic oscillations, and galaxy surveys all point to the same truth. The ocean is real, and its influence is growing. What remains unknown is its nature. Is it constant, forever stretching the cosmos? Is it dynamic, evolving in ways that may yet surprise us? Or is it false, doomed to collapse into something deeper? The human mind struggles to contain such scales. To know that the night sky is temporary, that the stars themselves are slipping into silence, is to confront fragility on a cosmic level. To imagine reality undone by vacuum decay is to glimpse annihilation without fire or flood, a rewriting of the rules themselves. To consider eternal inflation is to accept that most of creation is unreachable, that our universe may be one of infinite siblings forever apart. The escalation is not only scientific but existential. The ocean of energy that holds the universe together also holds its fate. It is at once cradle and grave, origin and terminus, silence and storm. And so the mystery deepens. Science has not ended it, but sharpened it. Every discovery expands the unease. Every explanation multiplies the paradoxes. The vacuum, once thought to be nothing, now appears as everything. And in that transformation, humanity finds itself adrift in a cosmos more fragile, more unstable, and more infinite than ever imagined. The storm at the heart of reality does not rest. It grows, it whispers, it threatens. The escalation is complete. The ocean is not merely mysterious, it is terrifying. The storm deepens, and with it rises the need for explanation. What is this ocean of energy? What is its origin, its substance, its fate? If the void itself is restless, then physics must search for language to describe it, models to contain it, equations to tame it. Yet here, at the edge of knowledge, the answers diverge. Each theory is a shard of possibility, a window into a deeper reality that may never be fully revealed. The simplest proposal begins with Einstein's cosmological constant. In 1917, seeking a static universe, Einstein added a term to his equations of general relativity, a constant energy density pervading space, pushing outward. When expansion was discovered, he abandoned it, calling it his greatest blunder. Yet decades later, with the revelation of accelerating expansion, the constant returned. Perhaps the ocean is unchanging, a fixed pressure built into the geometry of space-time, elegant in its simplicity, yet troubling in its silence. For, if constant, why this value? Why so small compared to quantum theory's vast predictions? The cosmological constant explains the observation, but not the mystery. Others propose a more dynamic sea, quintessence. In this vision, the vacuum is not a constant, but a field, an evolving entity whose energy density shifts with time. Like a tide rising and falling, quintessence could vary across epochs, mimicking dark energy's push. It introduces a living quality to the void, but it demands mechanisms, interactions, and unknown particles that remain elusive. The ocean becomes not still water, but a restless current, flowing unseen through cosmic history, a more radical framework. Arises in supersymmetry SUSY. In standard quantum field theory, every particle contributes to the vacuum's energy. The sum explodes into absurd magnitudes, minus 10,120 times larger than reality allows. Supersymmetry seeks balance. For every known particle, a heavier twin exists. Their contributions cancel, restoring harmony to the ocean. The vacuum becomes delicately tuned, its fury subdued. Yet supersymmetry's particles have not appeared in experiments, even in the high-energy collisions of the Large Hadron Collider. Without them, the ocean remains unbalanced, its paradox unresolved. Beyond supersymmetry lies string theory, a vision where particles are not points but vibrating strings. In this framework, the vacuum is not singular but multiform. Each possible vibration, each configuration of compact extra dimensions creates a distinct vacuum with its own laws and constants. The landscape of possibilities stretches into staggering numbers, perhaps 10,500 or more. Our universe is but one valley. In this vast terrain, its ocean of energy selected by chance or by survival. String theory transforms the vacuum into a multiverse of seas, each unreachable, each unique. But the cost is humility. Why this ocean and not another? Why a vacuum that permits galaxies and life instead of chaos? Some physicists turn to the holographic principle. Inspired by black hole thermodynamics, it suggests that information within a region of space is encoded on its boundary, like a hologram projected from a surface. If true, then the ocean of energy we perceive may not reside within space at all, but on the cosmic horizon itself. The vacuum would be a projection, its currents the shadow of deeper laws inscribed at the edges of reality. In this view, space-time and its ocean are illusions woven from information. Yet what generates the code? Who or what writes the horizon? Another approach lies in loop quantum gravity, LQG, which abandons the continuum of space-time for a granular vision. Space and time, in this model, are quantized into loops, woven like a network of discrete threads. The vacuum, then, is not continuous energy but the emergent result of this quantum geometry. The ocean would be a mirage, the macroscopic face of a lattice, too fine to see. If so, then the storm that fills the void is not truly energy, but the vibration of geometry itself. Still others contemplate the most unsettling scenario: false vacuum decay. Our current vacuum may not be the deepest possible state. A truer ocean lies beneath, lower in energy, waiting in silence. If transition occurs, it would rewrite physics itself. This speculation is not idle calculations of the Higgs bosons. Mass suggest our vacuum may indeed be metastable, balanced precariously between permanence and collapse. The ocean, we know, could vanish in an instant, replaced by one unrecognizable. Reality itself would drown. And yet, speculation does not end there. Inflationary cosmology suggests that the ocean once drove space to expand faster than light, smoothing and flattening the cosmos. If inflation never ends everywhere, then eternal inflation ensues. Universes bubble endlessly from the ocean's energy, each with different constants, each unreachable. We are adrift in a multiverse, an archipelago of infinities, each held in its own storm. Such visions raise philosophical questions as profound as the physics. If countless oceans exist, why this one? If the vacuum is dynamic, why now? Why do we live at the precise moment when dark energy dominates, but stars still shine? Some call it the cosmic coincidence problem, a riddle that seems to place humanity at a privileged moment in cosmic history. Is it selection bias, or a deeper law? Others go further, imagining that the ocean of energy is not merely physical, but ontological, the condition for existence itself. If the void is never empty, if fluctuations always stir, then perhaps somethingness is inevitable. Perhaps the true law of the universe is that nothing cannot be. The ocean would not be a property of space, but the root of reality, the pulse that ensures creation never ceases. Each theory is provisional. Each carries elegance and terror. The cosmological constant offers stability, but no explanation. Quintessence animates the void, but demands unseen fields. Supersymmetry promises balance, but hides its evidence. String theory expands the canvas to a multiverse too vast to test. Holography reframes the question itself, making the ocean a shadow of unseen code. Loop quantum gravity transforms it into geometry. False vacuum decay renders it a ticking clock. Eternal inflation makes it infinite. In this chorus of speculation, one truth resounds: the ocean cannot be ignored. It shapes galaxies, bends light, defines the fate of the cosmos. Whether constant or changing, true or false, finite or infinite, it is the silent architect of everything. The search for its nature is not only a question of physics, but of existence. And so the horizon of knowledge stretches as boundless as the ocean itself. Perhaps the ultimate theory will unify these fragments into clarity. Perhaps it will not. Perhaps the vacuum is forever paradoxical, its essence beyond capture. In either case, the ocean remains, the storm that never ceases, the tide that holds the universe together, and perhaps apart. The ocean of energy is too vast to touch, too subtle to see, and too fundamental to ignore. If it governs galaxies and whispers through atoms, then science must pursue it with every tool at its disposal. Humanity cannot wade into the void, but it can build instruments that listen to its tremors, machines that peel back its silence, observatories that map its shadows. The search for the vacuum's secrets has become one of the greatest enterprises in the history of thought, a campaign stretching from the smallest laboratories to the grandest telescopes, from caverns carved beneath mountains to satellites drifting through space. The journey begins with particle accelerators, the modern cathedrals of high-energy physics. At CERN, the Large Hadron Collider (LHC) smashes protons together at nearly the speed of light, recreating conditions a fraction of a second after the Big Bang. In 2012, it revealed the Higgs boson, a ripple in the Higgs field, itself a piece of the ocean that grants mass to particles. Yet this discovery raised new fears. Calculations of the Higgs mass suggest that our vacuum may not be entirely stable. Deep collisions at the LHC test whether the Higgs field rests in a true ground state or balances precariously atop a false vacuum. Each experiment is more than the search for exotic particles. It is a probe into whether the ocean beneath existence is permanent or doomed to collapse. But accelerators are only one frontier. In quiet laboratories, physicists measure the most delicate forces, testing the Casimir effect. When two metal plates are placed micrometers apart in a vacuum, they are drawn together, not by air, nor charge, but by the quantum fluctuations of the void itself. Improved experiments refine these measurements, turning whispers into data, mapping the contours of the invisible ocean. Every nanometer of precision is another question asked of nothingness. Yet Earth alone is not enough. The ocean's largest movements are written into the cosmos itself. Astronomers gaze outward with colossal surveys. The Vera C. Rubin Observatory, soon to begin its mission in Chile, will scan the entire southern sky every few nights, recording the drift of billions of galaxies. Its data will trace how cosmic structures grow and fade, revealing the fingerprints of dark energy. If the ocean's tides are changing, Rubin may be the first to detect their rhythm. Above the atmosphere, new eyes prepare to see farther. The Nancy Grace Roman Space Telescope, set for launch in the coming years, will study the expansion of the universe through thousands of distant supernovae. These dying stars, exploding with predictable brightness, serve as cosmic lighthouses. By comparing their apparent dimness, Roman will chart how the ocean of energy stretches space across time. Each flicker of ancient fire becomes a report from the storm. Meanwhile, the Euclid mission, launched by the European Space Agency, has already begun mapping billions of galaxies across vast swaths of sky. By combining visible and infrared light, Euclid will measure how dark energy bends geometry itself. It will peer into the scaffolding of dark matter, the invisible web upon which galaxies hang, and ask how this web is twisted by the ocean that drives expansion. Yet perhaps the deepest maps lie not in the present universe, but in its birth. The cosmic microwave background, CMB, is the faint afterglow of the Big Bang, a bath of ancient light that carries subtle imprints of quantum fluctuations. Missions like COBE, WMAP, and Planck revealed its patterns with increasing precision, showing how the ocean of energy seeded the first galaxies. Now, the next generation, Light-Bayard and CMBs-4, will search the polarization of this light for signs of inflation. The colossal surge of vacuum energy that expanded space in the first instant of time. If detected, such signals would confirm that the ocean once raged with unimaginable force, sculpting the very shape of existence. Physicists also listen in a different register, through gravitational waves, ripples in space-time itself. First detected by LIGO in 2015, they have revealed the collisions of black holes and neutron stars. But scientists dream of hearing fainter, older notes, primordial waves from the vacuum's earliest fluctuations. Future observatories like LISA, a space-based interferometer stretching millions of kilometers across, will tune to these frequencies. If they exist, these echoes may be the ocean's first cry, preserved in space-time since before galaxies were born. On Earth, ingenuity has crafted analogues of the void. In ultra-cold laboratories, researchers create Bose-Einstein condensates, states of matter cooled nearly to absolute zero. Within these fragile systems, they simulate event horizons, watching how vacuum fluctuations give rise to faint radiation, a laboratory echo of Hawking's prediction for black holes. These tabletop experiments suggest that the ocean's mysteries are not unreachable abstractions, but principles that can be glimpsed, even recreated. Under the right conditions, computation has joined the arsenal. Supercomputers simulate universes born from quantum fields, modeling how variations in vacuum energy would sculpt galaxies, stars, and voids. By comparing these synthetic universes with actual surveys, scientists test which versions of the ocean could be real. Thousands of digital universes flicker within machines, each one a hypothesis, each one a possibility weighed against the sky. Every tool converges on the same paradox. The ocean exists, but its depth is unknown. Theory predicts energy so vast it should tear the cosmos apart. Observation reveals a gentle push, barely sufficient to accelerate expansion. This gap, the cosmological constant problem, remains the worst mismatch in science. The experiments are not only measurements, they are acts of desperation and hope, questions flung into the dark. Why is the ocean so small? Why is it tuned so perfectly to allow stars, galaxies, and life? The urgency is real, for the universe changes even as we observe it. In billions of years, the sky will empty, galaxies fleeing beyond visibility. The ocean of energy will stretch them into darkness, erasing the map of the cosmos. The tools of today are not only instruments of discovery, but instruments of preservation. They are humanity's attempt to record the ocean's face before it vanishes from sight, and yet humility lingers. Each collider, telescope, and detector captures only fragments. The ocean reveals itself, not directly, but through consequences, the pull on plates, the flicker of ancient light, the drift of galaxies, the faint whisper of radiation. Science builds nets of steel and glass, but the sea remains untouchable. Still, this is the nature of progress, to reach for what cannot be held, to measure what cannot be seen, to ask questions that may never be fully answered. The frozen ocean is not merely a subject of study, it is the horizon of knowledge itself. Each experiment, each mission, each simulation is a step toward understanding the unseen tide that holds the universe together. And so the work continues. Machines hum in caverns. Satellites align their mirrors to the dark. Computers model unseen worlds. Humanity listens, waiting for the ocean to speak. In the beginning, humanity looked upward and saw only darkness, punctured by the scattered fires of stars. The sky seemed silent, eternal, infinite. Yet through centuries of questioning, it was revealed that this silence was not empty at all. Beneath the stars lies an ocean, invisible, unmeasured, yet everywhere, binding galaxies and whispering to particles, holding reality together. Now, at the edge of knowledge, science confronts the paradox. The vacuum is alive, restless, a sea of energy woven into the fabric of existence. And yet it is unknowable in its fullness, refusing to yield its measure, defying the laws we write. It is both cradle and threat, the foundation upon which galaxies shine, and the storm that could unravel them. What does it mean to live in such a cosmos? To dwell within an ocean too vast to cross, too deep to sound? The question is not only physical, but existential. If the vacuum is eternal, then reality rests upon an infinite tide, steady and unbroken. If it is false, a metastable pause, then existence itself is fragile, a bubble that could burst without warning, erasing all memory, all light, all history. This tension is more than scientific. It is philosophical, even spiritual. Humanity has always sought permanence in stone monuments, in myths, in the permanence of stars. But physics whispers otherwise. Permanence may be illusion. Beneath every structure lies fluctuation. Beneath every galaxy lies motion without rest. Even nothingness itself refuses to be still. And yet, perhaps it is precisely this fragility that grants meaning. A universe that could collapse is a universe alive. A cosmos that hides its depths is a cosmos that demands wonder. If the ocean of energy were fully mapped, if its every secret were revealed, would mystery itself vanish? Would awe wither, replaced by certainty? The unknowable, in its silence, preserves the sacred. Consider the symmetry. Human life mirrors the vacuum. Each person drifts between presence and absence, between what is seen and what is hidden. Just as particles flicker in and out of existence, so too do lives appear, vanish, and leave echoes in memory. The ocean that sustains galaxies sustains. Meaning itself, a reminder that nothingness is never truly empty, that silence is never void. Philosophers once asked whether the universe was infinite or finite, eternal or fleeting. Now physics offers a subtler vision. It is not simply the cosmos that holds mystery, but the void itself. The unseen sea beneath all things is as real as the stars, as decisive as time, as omnipresent as gravity. To live within it is to live. Inside a paradox, cradled by nothing, sustained by silence. In this reflection, one finds a strange comfort. The ocean that holds the universe together also holds us. Every atom in every body is tuned by its energy, granted mass by its fields, shaped by its currents. We are not separate from the void. We are children of its storm, eddies of its fluctuations, brief ripples upon its surface. But the question lingers: is the ocean eternal, or is it transient, a pause before collapse? Science cannot yet say. Perhaps it never will. The constant problem stands as a monument to humility, reminding us that reality exceeds the reach of equations. Predictions fail, models falter, and the ocean remains. There is terror in this. If the vacuum is unstable, then all we know is temporary. The universe could be rewritten in an instant, physics itself rearranged, atoms dissolved, stars extinguished. There would be no warning, no escape. The ocean that cradles us could also drown us. But there is also beauty, for fragility does not diminish meaning, it deepens it. To exist within a precarious cosmos is to exist within urgency, to find value. Not in eternity, but in the fleeting. Galaxies spin, stars burn, minds awaken, all upon a foundation that could vanish. The very improbability of stability makes its gift profound. In this sense, the ocean of energy is not only a physical truth, but a metaphor for existence. We are held by what we cannot see, moved by forces we cannot touch, sustained by balances we cannot control. Life itself is a storm held in fragile equilibrium, no less precarious than the vacuum. And yet, it persists. The closing image returns to the sky. The stars are not solitary beacons, but islands adrift upon an unseen tide. Their light travels through currents we cannot feel, shaped by a sea that will outlast them. One day, the galaxies will vanish beyond horizons, carried away by the ocean's expansion. The map of the universe will fade, leaving only darkness where there was once fire and humanity. What then? Even as the sky empties, the memory of it will remain. Our maps, our equations, our questions, they are records not only of what the universe is, but of what it means to know. To chart the void is not to conquer it, but to participate in its mystery. The ocean of energy may forever withhold its deepest truth, but in reaching for it, we discover our own. Perhaps this is the lesson. The void is not absence, but presence. It is not silence, but hidden music. The universe is not held together by certainty, but by mystery. And mystery is not a boundary, it is a horizon. The ocean endures, galaxies drift upon it, stars burn because of it, life arises within it. And though it may never reveal its full depth, it is enough to know that it is there, unseen, unmeasured, but holding all things together. So the story ends, not with resolution, but with reverence. The ocean of energy is the quiet heartbeat of the cosmos, the silence beneath sound, the darkness beneath light. To live within it is to live inside a riddle. To know it exists is to know that reality is stranger, deeper, and more beautiful than we ever imagined. The sea holds the stars. The sea holds us. And still, the sea remains.